Alright, so now we know how to take the derivatives of products of functions. Now we need to figure out how to take the derivatives of quotients of functions. Well, I'm going to leave the derivation for this quotient rule till the end of this video. You don't need to watch it because it's similar to the one for the product rule, but it's really a bit more work and it's not as pretty. So instead, I'm just going to go cut straight to the chase and just show you what the quotient rule says. In terms of thinking of it as a ratio of two variables depending upon x, the derivative of u divided by v is u prime v minus uv prime over v squared. It looks a lot like the product rule upstairs, except I have a minus instead of a plus, and also I have to divide by v squared. In function notation, the derivative of f divided by g is f prime g minus fg prime over g squared. That's the quotient rule. So now we can take the derivative of any rational function. So for example, let's let y be equal to 2x squared plus 1 over 3x minus 2 and find y prime. We're going to apply the quotient rule with f of x equal to the numerator, 2x squared plus 1, and g of x equal to the denominator, 3x minus 2. So we take f prime g minus fg prime over g squared. The derivative of f is, well, the product rule says the derivative of x squared is 2x. So we have 2 times 2x, which is 4x. And the derivative of a constant is 0. So that's just 4x times g, 3x minus 2, minus f, which is 2x squared plus 1, times g. G is 3x minus 2. The derivative of 3x is just 3. The derivative of 2 is 0, so I'm left with 3. And that's all over g squared, which is 3x minus 2 squared. I've taken the liberty of just going ahead and doing the algebra. You can do the simplification yourself. Oftentimes, we really like to leave the denominator factored like this, though. It just makes things a little bit easier if we continue to take more and more derivatives. So if you wanted to, you could multiply it out, but I'm going to leave it like this. All right, another example. Let's let g of x be e to the x plus 1 over e to the x minus 1. Let's find g prime. Let's apply the quotient rule. This time I'm going to let u and v represent the numerator and denominator because I've chosen g to represent the whole function. So u is e to the x plus 1, v is e to the x minus 1. So the derivative of g is going to be u prime v minus uv prime over v squared. All right. The derivative of u, e to the x plus 1, is just e to the x plus 0, so just e to the x, times e to the x minus 1, which is v, minus u, which is e to the x plus 1 times the derivative of v. Derivative of e to the x is, again, e to the x, minus derivative of 1, which is 0, so just e to the x, all over v squared, which is e to the x minus 1 squared. I went ahead and I simplified out the top to get negative 2 e to the x. You can go ahead and do that yourself too. But again, the bottom, I like to leave it as just e to the x minus 1 squared. Okay, so we're going to see that our rules of differentiation often get combined. We might have, say, a quotient that involves a product, like this. So let's let s of t be t times sine of t over cosine of t minus 2t. So I've got a product upstairs and then a quotient. Let's find s prime of t. So again, the derivative of the top here is going to require the product rule. So the quotient rule says take the derivative of the top times the bottom. The top is a product, so I have to do the product rule, which says I take the derivative of the first guy and leave the second guy alone. So the derivative of t is 1, I leave sine alone. Then I leave t alone, and I take the derivative of sine, which is cosine, and I add those together. This expression right here is the derivative of the top. Then I multiply that by the bottom, cosine of t minus 2t. That is just the derivative of the top times the bottom. Okay, now I subtract the top, which is t sine t, and multiply that against the derivative of the bottom, which is cosine. The derivative of cosine is negative sine t. And negative 2t has derivative negative 2. So that's that. Okay. That is all over the denominator squared. Cosine of t minus 2t squared. Great. I'm generally fine if you leave something looking like this. In fact, it's kind of nice because I can look and see what came from what. This clearly came from the product rule to me, and this looks like something that came from the quotient rule to me. However, going ahead and simplifying is a nice thing. Now I've done that, I get sine times cosine plus t times cosine squared, that's cosine times cosine, minus t squared cosine t plus t sine squared. That looks nice too, and if you want to go a little bit further, you can note that cosine squared plus sine squared is 1, so t cosine squared plus t sine squared is just t, and we end up with this more compact looking expression down here. Sine cosine plus t minus 2t squared cosine over cosine minus 2t squared. Now that we have the quotient rule, we can get the rest of the derivatives of the trigonometric functions, because they're all just ratios of sine and cosine. So let's do tangent. The derivative of tangent is the same as the derivative of sine over cosine, because that's what tangent is, sine over cosine. So I apply the quotient rule. The derivative of the top, sine, is cosine, times the bottom is cosine, minus the top, sine, times the derivative of the bottom is cosine, so its derivative is negative sine. And that's all over cosine squared, the bottom squared. I simplify the top. Cosine times cosine gives me cosine squared. Negative sine times negative sine gives me negative, negative, positive. Sine, sine gives me sine squared. That's still all over cosine squared. Well, cosine squared plus sine squared, you may or may not remember this, but this is a Pythagorean identity. Cosine squared plus sine squared is equal to 1. So I'm just left with 1 over cosine squared, but just to make things look a little bit nicer, 1 over cosine squared, well, 1 over cosine is the same thing. It has its own name. That function is secant. So 1 over cosine squared is secant squared. The derivative of tangent is secant squared. Remember that. Let's also do secant. So what is secant? Secant is the reciprocal of cosine, as I just said. So the derivative of secant is the derivative of 1 over cosine. One nice thing about the quotient rule is it allows us to take the derivatives of reciprocals of functions, 1 over a function. So I go ahead. The derivative of the top is 1, so I get 0 times the bottom, which is cosine, that's just going to go away. Minus the top, which is 1, times the derivative of the bottom, which is negative sine. Derivative of cosine is negative sine. And that's all over the bottom squared, so all over cosine squared. 0 times cosine goes away. Negative 1 times negative sine gives me sine over cosine squared. Now, if I have a ratio of products of trig functions like this, I can generally always rewrite it as products of just regular trig functions in the numerator. The way I'm going to do that here is I'm going to take 1 over cosine, just one of the cosines at the bottom, and write it as 1 over cosine. And then the sine I'm going to pair up with the other cosine from the bottom. Why? 1 over cosine is secant, sine over cosine is tangent. So the derivative of secant is secant times tangent. Commit that to memory. Okay, so here is question 2. Evaluate the derivative of cotangent and the derivative of cosecant. You can follow the same process that I did for tangent and secant, and it's very, very similar proofs. And just as I was able to show that the derivative of tangent is secant squared, and the derivative of secant is secant times tangent, you will be able to write the derivative of cotangent in terms of cosecant and cotangent, and the derivative of cosecant in terms of cosecant and cotangent. You're going to have to use trig identities, at least for this derivative right here, the Pythagorean identity. And to start off, you're going to have to rewrite these both as ratios of trig functions. Finally, as promised, here is the derivation of the quotient rule using the same color scheme as before. If you don't want to watch this, you don't have to. You're not going to be tested on this. It's not necessary to know, but it's enlightening. Okay, so delta U divided by V is what happens. It's the difference when I change x by delta x. Well, U divided by V, when I add delta x, becomes U plus delta U divided by V plus delta V. So the change is that quantity minus U over V. I get a common denominator, which gives me this expression, U plus delta U times V minus U times V plus delta V over V plus delta V times V. And then I multiply out. I get UV plus delta U times V minus UV minus U times delta V over V squared plus delta V times V. UV minus UV cancels out, so I'm just left with delta UV minus U delta V over V squared plus delta V times V. Then I divide by delta x. I divide here, and dividing here, I can just divide the numerator, and to divide the numerator, I'm going to divide each term, and dividing each term, I'm going to choose again to put the delta x underneath delta u and delta v. Why? Because now as I let delta x go to 0, delta u over delta x goes to u prime, there's the v, minus u, delta v over delta x goes to v prime. Now on the bottom, I've got v squared plus delta v times v, but delta v approaches 0 as delta x approaches 0. So I'm left with u prime v minus uv prime over v squared plus 0 times v. That goes away, and I'm left with the quotient rule.